Hello everyone, my name is Yanzhi Wang from Northeastern University. I'm going to record a video towards ultra-efficient deep neural network inference acceleration on the edge devices for the well-being applications. The deep learning is everywhere, including the self-driving, speech recognition, healthcare, and game playing, etc. However, it is not everywhere enough because the inference and training is time consuming and very much resource consuming. It's difficult for the real time to perform real time inference in the mobile and embedded devices. So a neural network typically has a large model sizes. It is projected that most of the deep learning systems, at least for the inference phase, will be deployed in the low power and embedded systems. For this kind of systems, they have limited form factor and power budget, and there needs to do a lot of work. It is often have multiple sensor inputs, forming a multimodal deep neural networks. For example, for the autonomous driving systems, it needs to have the video input and also needs to have the 3D radar inputs. And for many of the systems, it needs to have the audio inputs as well. So overall, the computation and the neural network size is much larger compared with the ImageNet. Furthermore, we need to satisfy the real-time performance requirement. It needs to react in the order of 20-30 milliseconds, otherwise it may be slower compared with a human being's reaction, and it may be considered to be dangerous. So this is a reason that people are working on the deep learning hardwares, including the GPUs, FPGAs, and dedicated ASIC chips. We were also working on it, and however, at this moment, we were working on the general purpose systems and how to accelerate achieving the maximum performance for this kind of general purpose systems. There is a research called the neural network model compression, which is becoming very popular recently. This tries to reduce the model size and reduce the amount of computation for the neural networks for acceleration. One of the representative technique is called weight pruning. Weight pruning reduces the number of weights and thereby computations. This is one type of the weight pruning, so-called non-structured weight pruning. It means that an arbitrary weight can be pruned, and the remaining neural network becomes a sparse neural network. We need index from one weight to index the next weight. So overall, this kind of sparse, irregular structure is very difficult to accelerate because doesn't match with the hardware on hardware parallelism for the GPU, CPUs, and other devices. So for this kind of neural networks, it often actually causes degradation in the speed because of the sparsity, and therefore it has very limited actual deployments. The question here is that if we can improve the compression rate, whether we can get actual advantages or actual acceleration. If this is not the best way, then what is the way of doing it? We will introduce our ADMM-based weight pruning and model compression techniques. So what is ADMM? ADMM is alternating direction methods of multipliers. It is an effective mathematical optimization by decomposing an original problem into two subproblems, and both subproblems can be solved efficiently. If we can consider an optimization problem fx plus g of x, we minimize this x. In ADMM, the first step, we're going to write it into fx plus g of z, subject to the constraint x equals z. It looks a little bit silly because if x equals z, then why do we need to separate this x and z? Because in ADMM, we're going to decompose this into two subproblems, one on x and another one on z, and they are going to be solved iteratively until convergence. The first subproblem is minimize f of x plus q1x given z. Here, we are given z, and we are going to find x. This q1 is actually a quadratic function. So this problem is the same complexity as the original problem. The original problem is the neural network training problem that minimizes a loss function, and now it has the same complexity of minimizing the loss function plus a regularization. The second subproblem is minimize g of z plus a quadratic term q2z given x. Here we are given x and we found z, and this subproblem has optimal solution, which is optimal solution for this kind of clustering-like problems. So we can see the result of the non-structured weight pruning. Here is the results on AlexNet for the ImageNet dataset. We can see the y-axis is a top 5 accuracy. Now it is not good to use 80% again as a top 5 accuracy, but we can go to 83%, 84%. And the x-axis is the overall weight pruning rate. We can see with over 60 times weight pruning, our accuracy is similar as their initial accuracy of the prior work. With almost 100 times weight pruning, our accuracy is still okay, while the prior work, their accuracy collapsed. So because of this significant gap, we can see the clear benefits of our ADMM-based weight pruning. We can see the result on IMNIS, where we can reduce the number of weights by 700 times, and there are only 600 weights remaining. So if we consider one IMNIST impulse, which is 28 by 28, 784, this is even larger compared with the remaining 600 weights, so we can see we're approaching the limits. If we can see the ImageNet, we can see the results before, and also VGGNet and ResNet. Notably, for the ResNet, we can prune about 9 to 10 times the number of weights while maintaining accuracy, or we can reduce 17 to 20 times the number of weights with less than 1% degradation in the accuracy. So we have demonstrated the advantage of our frameworks. Then we can see the application on the pneumonia diagnosis and localization. So for these applications, we're applying deep learning on the chest X-ray. So this is a text image embedding network. And the major challenge is for the low power embedded and mobile devices. So the model design is based on the YOLO v3, where this YOLO is a classical object detection network, and this network architecture is shown here. So the weight initialization for the backbone is a darknet 53 on the ImageNet, and the output tensor dimensions and the anchor boxes we can see shown here. So this is the structure of the model design, which is inherited from the YOLO v3 or v4 structures. And we can see the evaluation on the model pruning results. We can see using our pruning, which is a structural pruning of the filter and column pruning, we can reduce 36 times the number of weights or computations without accuracy loss, and we can reduce over 50 times the number of weights with a minor accuracy loss. We can see the original parameter set is over 60 million, and then after this kind of compression of the framework, the parameter set is between 1 million to 2 million, and then the accuracy can still be maintained. But even doing this may not be enough. We need to consider the actual acceleration on this kind of mobile and embedded devices. If we can test on a neural network like VGG16, typically it requires over 1 second on the state-of-the-art acceleration frameworks like TensorFlow, and takes over 300 milliseconds on TVM from University of Washington. This is very difficult on the further accelerations if we just use with pruning or quantization. But we have a solution. This not only focusing on how to derive the width of pruning, but also we are going to focus on the structure or the form after the with pruning. We are proposing the novel pruning schemes, which is a combination of pattern pruning and connectivity pruning. Previously, people believed that non-structured pruning is more accurate, but it is not very hardware friendly. While structured pruning is hardware friendly, but it is not accurate, and people think that this is an essential trade-off. But we think that this is not the case. Width pruning can be desirable, both at the accuracy and at hardware acceleration, or it can be desirable at all of theory algorithm compiler. And hardware levels, this is with the help of the compiler code generation. We can potentially enable real-time execution or close to real-time execution of all deep neural networks. So this is a structure of the pattern pruning. We can see this is different convolution filters, and for each convolution filters, we use as an example. So for each convolution kernel, we can either prune it. This is shown as a gray kernels, or we can assign a pattern, which is shown as a 4-input pattern here. So within the patterns, take arbitrary values, and they should be trained. The remaining weights are actually pruned, and these values are 0. Each kernel can assign a specific pattern, and we need to train to assign these patterns and also train the weights on these patterns. So at the theory level, this matches with the brain's cognition systems. The kernel shouldn't be square, only square, because this may causes some overfitting. And if we are going to use this kind of pattern-based structures, it actually enhances the recognition or the feature extraction capacity. And at the algorithm level, we can observe the algorithm improvements whenever we apply these patterns. So like we can see here, this is the actual improvements. After we directly apply this kind of patterns, the accuracy directly improves. And at the compiler level, although the patterns look still unstructured, but it is not actually unstructured because there are limited number of patterns, and the compilers can group the same patterns together and assign the same pattern to one thread and assign the thread to one computing core. And in this way, we can maximize the instruction level parallelism. There shouldn't be any parallelism degradation. And finally, the 4-input patterns is especially compatible with a single input multiple data or SIMD architecture of the embedded CPUs and GPUs. So this kind of structures is especially suitable for the mobile CPUs and GPUs. So here is a compiler-assisted inference acceleration framework for the pattern of block space pruning. We got the graph models from the TensorFlow Caffe2 PyTorch ONNX, and then we use the graph-based optimizations and other compiler-assisted optimization frameworks. What we can get is C codes for the CPUs and OpenCL, OpenGL codes for the GPUs. And then we got ready for the executions. All of this code are automatically generated. So what we can achieve on the smartphones. This is the results we compare on VGG, ResNet, and MobileNet with some baseline frameworks like TensorFlow Lite, TVM, and ADMM, Alibaba ADMM. What we can get is less than 19 millisecond inference time on VGG16 without loss of accuracy. This is 56 times speed up compared with TensorFlow Lite, over 16 times speed up compared with TVM, and over 13 times speed up compared with Alibaba MNN. We got 17.5 millisecond inference time on the ResNet 50 and 4.6 millisecond inference time on MobileNet V2. So recently, what we can get is 130 millisecond on BERT and 200 millisecond on GPT-2, which is the early version, previous version of the recently the largest neural network GPT-3. So potentially, because GPT-3 is not released, so we cannot see how fast it gets at this moment. So potentially, we can get the real-time execution of close to real-time execution of all deep neural networks. We can see some examples. This is the COVID-19 detection. We can see this is on the smartphones. This is some of our new results, not only the pneumonia, but also the COVID. We can see this is a healthy lungs. Oh, no, this is COVID. This is the pneumonia, but not COVID-19. And then this is the healthy lungs. And also we can have some similarizations, like, not only detection, but also localize where the COVID or the pneumonia is. Okay, that's specific localizations. And we can show some other results on the smartphones. Real-time automatic style transfer. We can see from the outputs, and then we can achieve the automatic and real-time style transfer when changing the different styles. You can see previously this is style 0, and then this is a new styles, etc. And here is the automatic resolution upscaling. The input is a lower resolution, and then which is shown on the top. And then we're going to change it to the high resolution, which is shown at the bottom. And then coloring. The input is a black and white video, and then the output is automatic coloring. And recently we can achieve what this is clearly cannot be achieved before. This is a YOLO V4 object detection. What we can achieve, this is 55 milliseconds per frame using our framework. And this is outperforming the TensorFlow Lite by 12 times speed up. And this is the first time that a YOLO V4 object detection can be achieved real time. And this can be applied for the auto driving and also for the UAVs and even for the animals. And also we can see here, this is a UAV angle. For some other examples, see the background substitutions. This is a background substitutions based on the UNet. And then we can see we can change to whatever the background is. And then we also show an example of the 3D activation detection. This is clearly beyond the capability of the prior work. We can achieve only 9 milliseconds per frame using our framework. And then this is outperforming the prior work by 30 times speed up. And then we have more demonstrations and more applications on our YouTube and Bilibili channels. So thank you. So you can email me, or you can see our demos at the YouTube and Bilibili demos, and as shown on these links. Thank you very much.